my dear student, I'm Mr. Actuala from Educare TZ. I will be with you in physics for Form 5. And today, my dear student, we are going to proceed with our discussion on our topic of rotation of rigid body for our subtopic of the center of mass. This should be the first subtopic on our session here. So, my lovely student, before we proceed with our discussion here, we are supposed to remember what we tried to see on the last session. On the last session, my dear student, we tried to see some examples related with what we tried to see on the past sessions. We see the position vector of the center of the masses. Those the question that was related due to the two coordinate put out to that occur into the two dimension. That is what we tried to see on the last session. We try to look only two examples of this center of masses. And today here, we are going to continue with our discussion for the total masses. Now we are going to see how can we find the total masses of the center of the body. So the total mass of a rigid body can be expressed in terms of the individual masses of this summation. So in order to represent the total mass of the rigid body, we must write it in terms of the individual masses. Kwa hiyo tuweze kurepresent ile total masses ya rigid body, lazima tuweze kuexpress in terms of the individual mass of this one. That can be the summation of this. So we try to see summation of I is equal to 1 when I start from 1 up to n, to the n stems, when we have so many masses. So therefore, from the equation number 4.3, now we should recall our equation number 4.3, which give us the center of mass of the rigid body, which can be expressed here. So the thing that we should consider is the equation number 4.3, the equation number 3, that give us the overview about the center of mass on the rigid body. And it can be represented in forms of this one. It can be represented in terms of this one, my dear students. So instead of using the summation of the masses here below, we are supposed to use the individual masses. Kwa badala ya kutumia pale chini kwamba ni summation of masses, tunachotakiwa tuweze kuapply pale itakuwa ni individual masses. And our formula here that represent the position of the center of the masses, it means LCM must be equal to the summation of mi times the vector Ri, but I start from 1 up to the n stems. It means up to the centenary value of n, as we try to observe here. So after that, my dear student, this should be the equation number 7 for our topic number 4. Here, the equation number 3 and also equation number 4, they are not differ more. Hizi ni kama zinafana, lakini kitu ambacho kinatofautisha nini? Instead of using the summation of mass I, we use the individual masses as we have been told into our statement. We should use the individual m. Kwa ndio maana tumepata kwamba LCM must be equal to the summation of mi times the Ra divided by the individual masses. So the center of mass in the xy, the center of mass in the xyz direction can be expressed in terms of this one. So imagine we have the xyz direction, and we want to express the vector, to express the center of masses. How can we express it, my dear students? We have been told that the center of mass I along to the xyz must be expressed in terms of this one. It means we should start with each coordinate. We will start for x coordinate, for y coordinate, and also for z coordinate. And for x coordinate, the center of the masses must be equals to the summation of mi Ri I starting from 1 up to the n divided by the individual masses, as we try to see here. But along to the y axis, it means the center of mass along to the y axis or along to the coordinate y must be equal to the summation of mass I times Ri, but I start from 1 up to the point n, as we try to observe. Along to the z coordinate, kwenye z coordinate na penyewe tutaliko vile vile kwamba yule center of mass along to the z coordinate must be equal to the summation of mass I times the vector along to the zi, then I starting from 1 up to the n stem z divided by the individual masses. So this should represent the equation number 8 on our topic number 4. Kwa hiyo hapa itakuwa ni equation number 8. So after there, my dear student, since the rigged body is a continuous, distribution of the particles or not discrete particles, equation 4 point here can be expressed as here. Because the rigged body is continuous, and if it is continuous, my dear students, we are supposed to express this equation number 8 on for our topic number 4 in terms of this one. Kwa tutatumia itakuwa sasa kumbe sasa this because it is continuous, it means it is not discrete. Kwa kama ni continuous na pia sio discrete, tunachotakiwa kufanya hapa, hatuwezi kuexpress kwenye terms of the summation, bali tuta express in terms of the integral. Kwa tuta apply integration ili tuweze kupata the center of masses for the continuous of the rigged body. So this x center of the xm must be equals to the integration of x dm times divided by m, but this m here is constant. Now we are supposed to factor out of the integration, and our equation should be the center of mass along to the x along to the x coordinate must be equal to 1 over m integration of the rigged body, integration of this x, then multiplies by the derivative of m. But along to the y-axis here, because it is continuous, our equation must be equals to 1 over m integral of y derivative of m. For finally, for the z coordinate, for z coordinate here, we should obtain that. We should obtain this z center of mass along to the z, along to the vector z must be equals to 1 over m, then integral of z times the derivative of mass, as we try to assume. So this equation here should be the equation number 9 on our topic number 4, and this come from the equation number 4.8. That is on 4.8 we have been given in terms of the summation, because the equation the rigged body was in the form of a discrete. Sasa kama inapokuwa ipo kwenye discrete, ipo kwenye continuous, we should express in terms of the integration, as we try to see. So after there, in general, the center of mass of the rigged body of continuous m can be expressed as this one. So generally, for generally sasa, we should express it in terms of generally. It means the center of mass of rigged body for the continuous must be equals to 1 over m, then integral of r times the dm times the dm. Where this equation come from? This equation, my dear student, come from this one. Imagine we have the R. Now we should sum this three equations. Tukishazi sum pale, tunachokifanya nini? dm ni common, tunamfact out. Basi kumbe tutabakiwa sasa, tunajua kasa kwamba R of cm must be equal to x of cm, then we add by y of cm, then we add by z of cm. But definition of the vector along to the x coordinate and also to the y coordinate and also finally to the z coordinate should be expressed in terms we have their definition. Now we should combine it together. How can we combine it? We should combine by saying that LCM must be equal to 1 over m ambayo ni common, then integration of bracket x it means x plus z plus x plus y plus x plus y plus z, then bracket or dm. But this derivative, this x plus y plus z integration wale ni summation ni sawa na r. Kwa tuta substitute r, mwisho wa siku tutaipata hii equation yetu kwamba kumbe the general formula of the center of mass for the rigid body of the continuous or not discrete must be equals to the 1 over m integral of the r dm. But this m here express the individual masses. So after they are here, let us go and look at the example. Let us see the example of this of what we tried to see on this session. We have our example number 4.3 related with what we tried to see. And our example said that find the center of mass of the uniform load of length L along its length. Here we have the load. We have the load ni kama rula. Those load, my dear students, contain the mass. The mass. Those uniform load contain the mass and they also having their length along its length. And we were supposed to find its center. Je, center yake itakuwa ni ngapi? Kama ile uniform load ilikuwa na length, ilikuwa na contain length na pia ikawa na mass. It means ukichukua ukaipima pale utapata ile mass yake ni ngapi ukipeleka kwenye beam balance. So how can we demonstrate the center of masses for uniform load? This is what we are going to see on our discussion, my dear students. So consider a uniform load solution. We have our solution and we are supposed to consider a uniform load with a small element dm. Tuashumu tuna load yetu. Sasa ile load ina uniform ina contain the element ambayo tunaita ni dm of length dx, lakini ina contain the distance of dx at a distance from the fixed point. So my lovely student, let us try to see here kwamba we have the uniform load and that uniform load having the small element ambayo ile small element tunaita ni dm. We can call it as the dm, and also it have the distance from the x where from the distance at it have the distance, small distance, it means in dx at distance x from the fixed point or the fixed axis of rotation here. So the mass dm can be expressed in terms of mass density. Kwa yule mass dm tutamu express in terms of the mass density. Now we can say that this dm must be equal to the mass density. It means tutamchukua ni sasa na mass divided by L, then we multiply by this small change, kale ka distance ambao ka small distance ambao kameongezeka along to the x from the fixed point. Kwa hiyo tutachukua equation yetu itakuwa ni hii hapa in terms of the mass density. So after there, my dear student, therefore from the equation 4.10 the center of mass of the load is here hapa. Kwa baada ya kudemonstrate sasa kwamba huyu mass dm, huyu small mass ambaye tumemsema ni sawasawa na ni sawasawa na mass density. It means ni sawasawa na mass divided by length times the small distance that at distance x from the fixed point. Now we should recall the question number 4 here, kwamba from this equation number 10 the center of mass of the rod is given as it is shown here. Kwa sasa kutoka kwenye question number 10, as we tried to see on the last session and we tried to express this mass density, unachotakiwa kukifanya hapa, chukua uniform load. Baada ya kuchukua uniform load, pale katikati ndio kwenye axis of rotation. Sasa pale kwenye axis of rotation place kwenye distance ambayo ni x, lakini kwenye x pale tuweke ka small change, ka change kadogo sana ka mass. It means ilipokuwa ina rotate ile uniform load kalikuwa kana bini formed, lakini pale kale kame exact kwenye dm, as we try to see when we demonstrate using the figure. So if it will rotate that small mass or yule dm atabini expressed in terms of the mass of the mass density. As we try to see that it should be given by taking the mass divided by the length of the uniform load multiplied by the small distance that have been increased there. So after this, my dear student, what we are supposed to do, the thing that we are supposed to do here is to recall that the center along to the x-axis, kwa sababu tunaongelea kuhusu kwenye x-axis, tutasema kuwa the center of mass along to the x-axis, along to the vector of the x-axis must be equals to 1 over m. Kwa tutamwambia ni sawa na 1 over m kama definition ambayo tulijaribu kuziona huku, kwa tutatumia hii definition kwa sababu ile uniform load ilikuwa inajaribu kurotate along to the x axis. So we should say that this center of mass of the rigid body must be equal to the integration, must be equal to 1 over m, ambao huu ni single masses. Then we multiply by the integration of this small of this distance from the fixed axis of rotation times the dm, ambao tutazidisha na ile dm, my dear students. But here this we are supposed, because our rigid body it is the continuous, kwa sababu ilikuwa ni continuous, ilikuwa ni not discrete, ilikuwa ni not sio discrete. Sasa tuta integrate from 0 to L. Kwa ile rula yetu sasa kutoka kwenye axis of rotation kwamba itaanzia kwenye original, ambao original yetu ilikuwa ni 0 mpaka kwenye center point itakuwa na rotate, lakini kwenye center point kumbuka L yetu alikuwa ni sawasawa timisi kwamba distance yetu alikuwa ni sawasawa na L. Kwa we should introduce those integration. But my dear student, we are supposed to say that this mass m, huyu m atakuwa the single masses must be equals to the L, ni sawasawa na length of the uniform load. Lakini yule dm tutamwambia kwamba mwenyewe ni sawasawa na small change of the x, kwa atakuwa ni ka small change of the x, watafanana. Kwa kama watafanana, sasa kinachotokea ni nini? Instead of writing in terms of this dm pamoja na m, tutamwambia ni sawasawa na 1 over L integral wa x, kwa sababu alikuwa na change along to the x hapa, ambao itakuwa sasa ni x alafu dx. And after there here we were supposed to integrate with respect to x, lakini from 0 is equal to L paka from 0 up to the L for the continuity of the rigid bodies. So if we integrate here, my dear student, we should put this dimension, and after integrating we should put this dimension as we try to see. If we integrate x with respect to dx, this x should be changed. It means itakuwa ni power ya n jumlisha 1, lakini n ni ngapi? N alikuwa ni 1 divided by n jumlisha 1, lakini n ni 1. Kwa tutapata sasa kumbe ni sawasawa na 1 over L, then those dimension wa x square over 2. lakini kumbuka tuna integrate from 0 to L. It means tutaweka L, it means itakuwa ni sawa na 1 over L, alafu akawa ni L square over 2 minus 0, it means minus 1 over L, minus 1 over L, alafu bracket wa 0 square divided by 2. So this should be, because here if we put L square watakuwa ni L wawili, lakini tukiliko kwenye exponent dimension exponent tuna the same base, tuna L square, pia chini tuna L, yule L atapungua, tutapata ni sawa na L over 2. Kwa hii sasa ndio itakuwa ni formula ya kutafuta ile load. Must be the formula of finding the center of a rigged body for a uniform load. So by saying that, my dear student, this is the end of our session here. Now I would like to welcome you again for another session. I wish you all of the best. Have a nice moment.